Hello everybody. This video is going to be a little shorter than normal. It's mostly a reminder of something you learned about in Honors Chem, is that we don't just care about the VSEPR shape because we love memorizing charts of names, right? We don't just love memorizing bond angles. The reason we care about the VSEPR is because it gives us information about how the structure of the molecule will affect the behavior. It'll tell us how things like lone pairs are acting, if it's polar or not, which will let us look at the behavior of the molecule. If you remember, the idea of VSEPR comes from the fact that the electrons want to repel each other, and that can alter the shape of our molecules. The pairs of electrons are going to try to get as much room as possible to minimize the feel of those repulsions. We have various shapes. Remember, you have linear. If you add an extra atom, they need to spread out. You get trigonal planar. You add one more atom. It's not going to be flat. It's going to have a 3D shape called tetrahedral. That gets us 109.5 degrees between our atoms instead of just 90. They'll feel less repulsions. If we add one more atom, you get trigonal bipyramidal or trigonal bipyramidal. 3 of the atoms will take what we call an equatorial position. They'll make a flat triangle in the middle. And we'll have an atom on top and bottom, which are called axial. If you add one more atom, you get what's called octahedral, where you have this flat square in the middle, this planar square shape here, equatorial, and then you have axial and axial. And they spread themselves out nice and far apart. You get all these 90-degree angles. A lot of teachers will use these balloons to show you that they will naturally spread themselves out, and that that's as far apart as they can really get without anything feeling crowded. We have to remember that lone pairs on the center atom can mess things up a little bit. They occupy a little more space than a bonded pair. Therefore, your bond angles will end up a little smaller than expected. So it's not that, we're memorizing our VSEPR shapes and we stop at that point. We have to know the general shapes and then be on the lookout for things like lone pairs, because that's going to show us that those atoms are going to get pushed down a little bit. We end up with a distorted bond angle. Now, if you want to think kind of in general terms about which combos of electron pairs end up with the most amount of repulsive forces, the lowest amount of repulsive forces would be between 2 bonded pairs. That's when you have your perfect bond angles, when all you have are atoms. If you add a lone pair to the center atom, it's going to have a little more repulsion to those bonded pairs. You get distorted a little bit. Something like NH3 has a lone pair on top, you get a little bit squished on your bond angles. If you have more than one lone pair, you're going to get a lot more repulsion. Something like water. It's bent and those hydrogens get pushed way down. Those lone pairs can really affect the 3-dimensional shape, which can then result in things being a little less than ideal. You can see here we have slightly smaller bond angles, and here even smaller. This can also result in a molecule ending up polar. Remember, polarity is a spectrum. On one end, we have perfectly nonpolar. Everything is being shared perfectly. Polar is when they're not being shared evenly. And if it gets to the point where it's so extreme that one atom is so electronegative that it literally stole the electron, then it's ionic. But those lone pairs and that VSEPR can really affect whether something is polar or not. That's why we care about VSEPR. That's why we care about lone pairs. It's because we want to know if something's polar or not, because that tells us how it behaves. Remember, there's 3 ways you can really show your dipoles. I like the arrow showing the overall direction. Remember, the dipole is the sum of all the little differences. What direction are those electrons going to be pointing in or being pulled in? I also like the little partial positive and partial negative symbols. Computer software can do these nice little bubble drawings. Please don't do these, okay, on your paper. They're really hard to draw accurately. You're not going to have color pencils on your AP exam, right? But we see these a lot when we're looking at computer software simulations. In order for a molecule to be polar, you have to have polar bonds, right? There has to be a difference in their electronegativities, but then you have to also measure like that appreciable difference. It has to actually sum in a direction that results in a slightly positive end and a slightly negative end with that asymmetrical shape. If you look here at our carbon dioxide, I have a slight dipole going to the left, I have one going to the right, but I don't end up with an overall dipole because they cancel each other out. This is hard to understand if you have not taken physics. In physics, you learn that these little arrows, these vectors, can add together. But if you think about the little cartoon pictures you saw in honors chem of your polar bear and penguin, if you think about you're being pulled in equal and opposite directions, the left and the right are the same, the top and the bottom are the same, you end up with no overall dipole on your molecule. Compare that to water, and you end up with the electron density being pulled upwards towards that oxygen, less electron density towards those hydrogens. Those little red arrows are adding together to give you an overall dipole for your molecule. It is important, very important, that on AP FRQs you don't just say things like, it's symmetrical. You have to say the dipoles of the bonds cancel out so that you end up with no overall dipole. That's important. They want to see that you understand that each bond is polar, but the directions are equal and opposite, and that your dipoles cancel out. So hopefully you remember these little cartoons, right? The more electronegative atom is our polar bear. It's pulling harder. Compare that to our carbon dioxide, where we see that poor little penguin pulled in equal and opposite directions. The dipoles cancel. Always double check to see if they're asking about a bond polarity or a molecule polarity. All of these top ones here, these 3, have polar bonds and are polar molecules because their dipoles do not cancel out. You end up with a net dipole, an overall dipole. Down here, the bond dipoles cancel out, and you end up with a non-polar molecule. Here, this one is easy to see, top and bottom the same, left and right the same. People struggle with trigonal planar, okay? I promise that trigonal planar is nonpolar. It's a little hard because people are not taught symmetry in as complex of a way as it actually is. So if you have a hard time seeing and understanding how those 3 dipoles cancel, just trust me, this is nonpolar. And once again, we're learning all this not just because we care about memorizing a VSEPR chart. It's not just because we care about memorizing names and bond angles for things, but it's because all of those tell us the polarity. And the polarity, while interesting in and of itself, is really important because it tells us about how those molecules interact with each other. Do you remember learning about your intermolecular forces? That's going to be a chapter we spend a lot of time on second semester, but we're getting a little reminder here that our polarity is important because it tells us things about the properties, the boiling points, the melting points, the solubility, all of those things, right? It really tells us how lone pairs are affecting those properties because of how they're affecting the shapes and because of how they're affecting that polarity. All right, everybody, I hope that was a good reminder of some of those honors chem things and how they'll come into play a little bit this year. All right, that's it. Bye.